So good morning all of you. So welcome to physics online session. In this today's class we will discuss an important chapter, that is semiconductors, and this chapter is very useful in your engineering courses. So the fundamentals, so you learn here in this chapter. So if you are good at semiconductor, then only you can understand various concepts in your engineering branches like EEE, EC and uh, CSE, etc. Okay, so here this chapter semiconductors we will talk about the electrical conductivities. So we all know that the metals are good conductors. Metals are good conductors, and we in all the household wiring and in most of the electrical circuits, okay, the connecting wires, we use connecting wires, that is copper. In connecting wires we see the material in the connecting wires and household wiring. So there is a copper is a good conductor of electricity. In olden days aluminum is also used. So, and because of aluminum the power losses are large. So nowadays we are using copper only. So in olden days, so it was used, but there was a lot of power wastage. Why? Because the conductivity of aluminum is much less than the copper. Okay, so and and the next class of materials that we see in our daily life are insulators. Insulators. Okay. Let me take one example. For example, I have a bulb. Okay, there is a bulb, small bulb. So I want to glue the bulb with the help of a battery. So I have a battery. Okay, this is a battery. It's a plus and minus, and so initially I have connected the bulb, the two terminals of the bulb to the battery. Okay, so when you switch on the button, when you close the key, the bulb will glow. Okay, if it is made of copper or any metal, okay, so we know that metals are good conductors. They allow the electricity to pass through them. Okay, so the bulb, when you switch on the key, immediately the bulb will glow. Okay, so now what happens? I'm replacing this copper. I'm replacing with copper with another material. Example of insulator, thread. Thread or plastic. Okay, thread, plastic, rubber, glass. These are the examples of insulators. If you replace the copper with a one rope, does the bulb glow? It doesn't glow. It doesn't glow. Because thread is a bad conductor of electricity. It does not allow the charge to flow through them. Okay, so it is a bad conductor of electricity. Okay, so examples of insulator. So why thread, so cotton, plastic, okay, rubber, glass, etc. These are the examples of insulator. Examples of metal, I already told, copper, aluminum, silver, nothing but Ag, and gold, nothing but Rm. Okay, these are the examples of metals. Okay, so now the another class of materials that is a present point of interest, that is we are talking about semiconductors. Third class of materials, those are called semiconductors. Okay, semi, so the name itself reveals that the conductivity of these materials are conductivity of Semiconductors, simply I'll write semiconductors are almost 10 power of minus 11 times the conductors. Their conductivity are much less than the the conductivity, electrical conductivity of semiconductor is 10 power of minus times smaller than the conductors. Okay, and there are a lot of power losses when you use semiconductor in place of conductors. Still, even though the conductivity of semiconductor is small, but these semiconductors are widely used. Semiconductors are very extremely used in various electronic devices, so like digital cameras, laptops, computers, mobile phones, washing machine. Okay, so wherever the control systems, so you will see, so in all the control systems we use these semiconductors, like sending rockets to another planet. So where we are controlling the conductivity. So in any control system, so we use these semiconductors. So why we are using these semiconductors? So here, so I told that the conductivity is very small. Actually, we don't know how to use this one, but even though its conductivity is very small, so they are widely used in a lot of modern day electronic devices. So because, but the little process of the semiconductors, we can control the conductivity. When someone controls the conductivity of a material, there will be lot of applications. That is why, so these semiconductors are very important and widely used in many of the modern day electronic components. So our life is entire life is revolving around these semiconductors only. So that is why this chapter is very important. So in the introduction class, so just we'll talk about the classification of materials. So we'll classify the materials. Already I told the three classification, but I will discuss what are the conductivities and resistivity of these materials here. So the classification of materials already we have discussed. So based on the conductivity and resistivity values, the materials are classified into three types. The resistivity, uh, represented by rho, conductivity represented by sigma, and the conductivity is the reciprocal of the resistivity. And these are the ranges of the resistivity and conductivity values of metals, insulators, and semiconductors. What I told, the conductivities of semiconductors and resistivity and conductivity values of semiconductors lies in between insulators and metals. Okay, this is about the classification of materials already discussed. Okay, so the next the slide. So we need to, what I told before going into the semiconductors, first we have to know what are the conductors and why the conductors are, why the metals are good conductors. Okay, so let us take one example. So according to Bohr atomic model, see, an isolated atom has well-defined energy levels. Okay, and this is an atom. If there are no other atoms present, let us take this is only one atom. Forget about the second atom. For an isolated atom, there are different energy levels. Okay, so well-defined energy levels. Let us take a hydrogen. So 1s2. There are different energy levels. So 1s2, s2, p3, s3, 3p, 3d. These are the different energy levels. Okay. So the energy of electron depends on the energy in which the electron revolves. Okay. So depends on the energy. So depends on the orbit number, the energy the electron possesses. Okay. So so here, so let us take an example of sodium, whose atomic number is 11. So this is electronic configuration. 1s2, 2s2, 2p6, 3s1. So here first and second orbits are completely filled. So 1s2s are completely filled. and third orbit is partially filled by only one electron. So here third orbit can accommodate actually 8 electrons. So there are 8 quantum states. Out of 8 quantum states, 8 energy states, out of 8 energy states, only one energy state is filled. Okay, so these are the energy levels. So 1s, 2s, 2p, 3s are this 1s, 2s, 2p are completely filled, and 3s is partially filled, and 3p, 4s, 4 remaining are unfilled energy levels. Okay, here s orbital has 2 energy states and 2 electrons are completely filled at the two quantum states. So this 2s also 2 quantum states, 2 electrons are completely filled. 2p, p orbit has 6 quantum states, 6 electrons are completely filled. Here 3s contains 2 quantum states, so one is one, only one is filled here. Okay, it is partially filled. This is for isolated atom. If this is for an isolated atom. If you uh, if we have a sodium vapor, okay, so these are the energy level picture when there is a when you have only one atom. Okay, so and then if there is a sodium vapor, for example 1 gram of a sodium vapor contains Avogadro number of atoms, and these are the energy levels, same energy levels. Okay, so but there are group of energy levels, so each atom has its own energy level. So here even though in a vapor, so the atoms are the separation between atoms is very large, so one atom is not interacting other atom much. Okay, there is no much interaction between atoms, so they also possess the same energy levels with no difference. Okay, so then if you cool the sodium vapor, uh, then it becomes a solid. So if you take a solid sodium, the atoms come closer and closer, so very close. So electrons of one atom interacts with the nucleus of the other atoms. So here the interaction, so electron interaction here changes. Okay, so here so this is the nucleus, and these are the different energy levels. So if you have n atoms, uh, if you have n atoms, there are two uh, n electrons in the 1s state and 2 n electrons in the 2s state. Why? Because it can accommodate 2 electrons, it can accommodate 2 electrons, it can accommodate 6 electrons. Okay, so here there are 6 n energy states. Okay, and 6 n electrons are occupied here, 6 n electrons. Okay, so what happens here when the atoms are very close to each other? When atoms are very close to each other, interaction is changed. So the force of interaction experienced by this electron, outer electron, will differ. It will change. Okay, so this all 1s electron, so are very close to each other. According to Pauli's exclusion principle, no two electron can accommodate a single energy state. Okay, so here that is why they are grouped. These all n energy states. There are n electrons. Each electron has one s energy state. So all the energy states are grouped. Okay, so a group of there are series of energy levels, but the separation is very small. But because these inner electrons, so experience much interaction from this neighboring atom. Only this outer orbit experience appreciable interaction from the neighboring atoms. Not only one atom is present, so number of atoms are present about this atom interest. So that is why that is why some of the 3s energy levels goes up, some of the 3s energy levels goes down according to Pauli's exclusion. No two electrons can see the same energy state. That is why some of the 3s energy levels goes up and some of the 3s energy levels goes down. So it makes the series of energy levels. This is called energy band. This is called energy band. energy band. Okay, and these are loosely attached. Outer electrons are loosely attached. Those inner electrons are strongly attracted to the parent nucleus. This is loosely attached. Okay, so even with at a low thermal energies, this can become free and can start interacting with the neighboring atoms. Okay, so that is why. So this called this can become free. Okay, this is called free electron. Okay, so here this bond is called conduction bond, where we have valency electrons are these electrons are completely, sorry, this is called valency band and completely filled, and this is called conduction band, where you find free electrons. Okay, this is valency band and conduction band. There is a gap between valency band and conduction band, so there is no energy error in between them, so that is called energy band gap. Okay. So if you take another example, let us take a magnesium. Let's take a magnesium. So 1 minute. Let us take a magnesium whose atomic number is 12. 12 nothing but 3s2. Okay. This s orbital also completely filled. So I want to remove this one. This. Okay. So this is 3s. Not representing the lower energy levels, so 3s and 3p. So in case of a magnesium, atomic number is 12. So 3s, there are series of energy levels. Since there are a number of atoms, some of the energy levels goes up, some of the energy levels goes down according to Pauli exclusion principle. And this is 3p energy. These are 3s energy levels. Okay, and 3p also in the same orbit color. Yes or no? So these energy levels also split. Okay, so these are a series of energy levels. So this s orbit is completely filled for magnesium. So this now behaves like a valency band, and this is a conduction band. Almost they overlap because this is in the same orbit. 3p and 3s are in the same orbit, so they overlap. So I want to tell 2 points here. In some conductors, there is a gap between valency band and conduction band, which is very small. In some other solids, there are overlap. There may overlap. Conduction and valency band may overlap. This is the energy band structure in case of conductors. Now we'll discuss uh, semiconductors. Okay, let's see, before going to discuss semiconductors, let us see some energy levels. The energy levels, so the series of energy levels, some of the energy levels are going up and some of the energy levels are going down. All, so uh, no single electron, no two electrons can have the same energy level together. So different electrons have different energy levels. They form a series of energy levels that is called energy band. Okay, so and this band, the series of energy levels are band formed by valence electrons is known as valency band, and the band formed by conduction free electrons is known as conduction band. Okay, the band formed by free electrons is known as conduction band, and the band formed by valence electrons is known as valency band. Valency band is completely filled, whereas conduction band is fully empty or sometimes partially filled. Okay. So valency band is completely filled. Here, valency band is completely for magnesium. Valency band is completely filled. For sodium, so this is the valency band is completely filled, 2p orbital. Okay, but what about this conduction band? Conduction band is fully empty. So this is empty. 3p is completely empty, or sometimes it is partially filled. Okay. So the next one, let us discuss the energy level diagram of semiconductor. Let us take an example of semiconductors. Example of semiconductor is silicon. So this silicon contains n atoms. This contain n atoms. N atoms. For silicon, the outermost orbit is 3. So first, let me write the electronic configuration. Sorry, 1s2, 2s2, okay, 2p6, 2p6, 3s2, and 3p. Okay. The atomic number of silicon is that is equals to 14. So electronic configuration is 1s2, 2s2, 2p6, 3s2, and 3p4, 3p2, and the outer orbit contains 4 electrons. The outer orbit contains 4 electrons. Say 4 electrons. 2 electrons are in s state and 2 electrons are in a p orbit. 2 are s orbit and 2 electrons in a p orbit. Hence, there are, if you take n number of atoms, how many 2s states are there? How many 2s electrons are there? How many s electrons are there? 2. 2 3s electrons, 2 3p electrons. Totally 4 electrons. And we have n atoms. So then totally we have 4n electrons. So the max, but so this third orbit can accommodate, this p orbital can also accommodate 4 more electrons. Okay, actually there are 4 energy states which are empty. Okay, so actually it can accommodate 6 electrons. Okay, 6 electrons, and this is 2, totally 8 energy states. But out of the maximum possible number of electrons in outer orbit is 8 now. Okay, so this node can accommodate only 4 electrons. So okay, so 4 valency electrons are there and 8 energy levels. We have 4 electrons and 8 energy states. 2, and this can accommodate 6. 2 plus 6, 8 energy states. Out of 8 energy states, only out of 8 n energy states, only 4 energy states are filled. So now these 8 these 8 n energy states are split into two parts, okay, and separated by some gap that is called energy gap. Okay, so here the lower band, which is completely occupied by 4n electrons, is known as valency band. Okay, the other band that is above the valency band is known as conduction band. Okay, see here, this is a this is about 0 Kelvin. At 0 Kelvin, all these electrons, all these energy levels are completely filled. This is called valency band. This is a valency band, and this is a conduction band. Okay, so out of 8 energy states, and this 4 energy states are completely filled, and 4 energy states are completely empty, and there is a gap between the 4, and then is called energy gap. This is at 0 Kelvin. Okay, so at conduction band is completely empty at absolute 0. This situation is at absolute 0. As temperature increases, so one by one, slowly electrons can jump from valency band to conduction band. But at 0 Kelvin, so all electrons are in the valency band only. So here, the lowest energy level in the conduction band is represented by EC, and the highest energy level in the valency band is known as EV. See here, this is the lowest energy level in conduction band EC. Highest energy level in valency band is EV, and the distance between them is called energy gap. The gap between the top of the valency band and bottom of the conduction band is called energy gap. Okay. The distance between the top of the valency band, this is the top of the valency band, and bottom of the conduction band is known as energy gap. Okay. So now, depending on the forbidden energy gap, solids are classified into 3 types. Once again, I am classifying the same materials based on the energy gap: conductors, insulators, and semiconductors. So now I want to show the energy band diagram here. The energy bond structure in semiconductors are two types. Already I explained. In some conductors, the conduction and the conduction band and valency band may overlap in magnesium. Okay, I gave an example. Yes, sir. So when there is an overlap, electrons from valency band, when they overlap, so electrons from valency band can easily jump into the conduction band. So this makes large number of levels. electrons are available for conduction. So hence the conduction takes place. Okay. So in some conductors, valency band and conduction band overlap, so electrons can easily jump from valency band to conduction band. When electrons are present in the conduction band, so the electrons which are present in the conduction band are known as free electrons. Okay, so they are ready to conduct. Now, so this is the energy bond diagram. So here this is for conductors. In some conductors, the valency band and this valency band and conduction band overlap. Okay. In some other conductors, so there may be a gap between the valency band. So valency band is partially empty. This is partially empty, and there is filled, partially empty. Okay, and there is a gap. These two type of energy bond structure will be there in a conductor. When we have a valency band is partially empty, then this is a valency bond is partially empty, and electrons from its low energy can move to higher energy level responsible for electrical conduction. Okay, electrons from its lower energy can move to the higher level and responsible for electron conduction. In this type of semiconductor, electron from lower energy level can move to higher energy level. These are the unfilled energy levels, and these are electrons. These are filled energy levels. The electron can jump from this filled energy states to unfilled energy states, and they are ready for electrical conduction. This type of conduction takes place in semiconductors. When they overlap, so electron can easily jump from valence band to conduction band. Here, electrons can jump from lower levels of valence band to higher levels of valence band. Okay, so therefore, this type of materials have low resistivity and high conductivity. This is about conductors. In insulators, the gap is the forbidden energy gap is large. It is greater than 3 electron volts. So no electron in the conduction band, and there is no electrical conduction is possible. So here this gap is very large. Okay, very large. So require very high energies to even at higher voltages also, no electron can move from valence band to conduction band. So the gap is very large. So no electron can jump from valence band to conduction band. So no conduction, no electrical conduction takes place. Okay, this is about insulators. And for diamonds, the energy gap is about 5.5 electron volts. Okay, so very high. Semiconductors. In semiconductors, the energy band structure, you can see this is energy band structure. It is less than 3 electron volts. For conductors, it is less than 0.1 electron volts. For insulator, it is greater than 3 electron volts, and for diamond, it is 5.5 electron volts. And for semiconductors, diamond is a diamond is an example of insulator. In semiconductors, the forbidden gap is less than 3 electron volts. So because of the small band gap at room temperature also, some of the electrons can enter the conduction band from valence band. Okay. So these electrons can move in the conduction band, are responsible for electrical conduction. Okay. So because of the small energy gaps, okay, electron can move from valence band to conduction band, and they are responsible for electrical conduction. Okay, so forbidden energy gap for, remember these are important values. For germanium it is about 0.67 electron volt, and for silicon it is about 1.1 electron volts, and for gallium arsenic it is 1.41 electron volts. If you convert 0.67 electron volts to germanium semiconductor, so electron can easily jump from valence band to the conduction band, and they are ready for electrical conduction. And similarly for silicon it is a 1.1, and for gallium arsenide it is 1.41 electron volts.